Hi everyone, we are Team Acumentrics and this is FaultLine 2022, a continuation of a capstone project originally started in fall of 2019. Our technical directors include Brendan Smurbeck, graduate of URI class of 2017 and capstone alumni, Bill Owens, the overseer of the project, and Najib Ashak, our machine learning consultant. On our team, we have Matt McAdams, a computer engineering major with a minor in mathematics, and myself, Sean Maglione, also a computer engineering major with a minor in cybersecurity. This project is sponsored by Acumentrics, based in Walpole, Massachusetts. Acumentrics specializes in rugged, uninterruptible power supplies. Their products offer power conditioning, surge spike protection, and seamless automatic power backups. Acumentrics has been working with the ELECOMP Capstone program via the FaultLine project for 3 consecutive years. The motivation for this project is based in the emerging technologies that will allow for enhanced power consumption analysis and predictive maintenance. By sampling the voltage and current to determine power signatures, we can identify specific devices and how they operate under normal conditions. Using this analysis along with machine learning, we are then able to predict when maintenance is needed by detecting variances compared to the normal operating condition. This highly reduces the likelihood of catastrophic failure in connected devices. Our anticipated best outcome can be broken down into 4 separate stages. The first stage is expanding the general model to include additional electromechanical devices. The second stage involves improving the accuracy of this model through optimization and better data sets. The third stage is implementing on-device training, which utilizes the Jetson Nano, the embedded computing system within the Smart PDU. The fourth and final stage is demonstrating transfer learning by implementing a specialized, partially frozen machine learning model to improve the inference on additional devices. And here are the results. We expanded the general model to incorporate 2 devices, a bagless vacuum cleaner and floor fan. We also improved the accuracy of this model, reaching a final accuracy of 85% with various different fault states. We were also able to implement on-device training onto the Jetson Nano, which was the main challenge and most time-consuming aspect of this project. This works in real time with on-demand data. And lastly, since transfer learning is the act of applying the specialized on-device model to new devices with new fault states, this has not been fully achieved since, at the moment, it is limited to these 2 devices. A power signature consists of a set of data points of the power usage of a device. Power signatures can represent a device at a given state. Therefore, identical devices operating at the same state will have very similar power signatures. FaultLine focuses on simple electromechanical devices because it is easy to replicate these power signatures. They have recognizable and demonstrable faults, and they also have a strong potential for transfer learning. Here is a visual representation of recording power signatures from a device. I will now introduce Matt McAdams for an overview of machine learning.
Thank you, Sean. Now, using machine learning, we took all of our collected data, transformed it into a model that can determine the device that is plugged in, the functionality, and the fault state if faulty. This works by creating a virtual set of neurons, similar to the way a human brain is put together. We can set up as many neurons in as many layers as we want, but finding the right configuration is crucial to getting the best results. In the input layer, you have the incoming data, the power signatures we collected, the locations from which they were collected, and any other information we can think of. Through training, the model determines which inputs are important, adjusting the weights of each connection until it has a pretty good idea of what the incoming information means for the outputs. The output layer contains as many outputs as there are possible outcomes to the problem. In our case, 1 layer for each device and each fault state. To better train these models for individual scenarios, we implemented transfer learning. This means that we've taken the output layer of the model completely, frozen the lower layers in order for the model to continue learning and specializing itself to the equipment that it'll be working with, while maintaining its general shape and ability to determine outcomes. We firmly believe that this system will allow for a deeper understanding of our own projects that we, as engineers, were not capable of producing before.
Thank you, Matt. I contributed functional additions to the DAC, or data acquisition. I developed an on-device version which incorporates a circular memory buffer. I then created a shared Python library which is used for on-device training and transfer learning. I then implemented this library for inference. The circular memory buffer plays a key role in on-device training, as it allows for on-demand data. Since we are working with the limited resources of the Smart PDU's embedded systems, storing data to files is simply not efficient. By instead storing the data in a temporary buffer, chunks of data can be acquired very quickly with minimal data loss. I also contributed to the general model by improving our datasets. I did this by refining data collection and analysis. I designed and implemented a master data file to compile and organize data. I also implemented data quality control measures. I automated the data collection processes and added 3 new parameters to each data file: the physical location that the data was collected at, timestamps, and port numbers.
And we decided pretty quickly that we were going to have to set up a new working environment, since the image of the Jetson Nano we were given last year unfortunately couldn't keep up with the new demands of the project. From there, we rated different electromechanical devices based on important criteria, as Sean mentioned earlier, to determine the best fit for the product. We then decided on parameters to collect along with the power data from the devices. After collecting everything we needed, we fed the data through a 2-level model to differentiate between devices and then further determine whether the device was faulty or functional. Future work on this project would include further expanding the dataset to include a wider variety of devices and fault states. We'd like to thank Brendan Smerbeck for his dedication to leading us to success, Bill Owens for his oversight, and G.B. Schock for his crucial insight on machine learning, and most of all Dr. Harish Sunak for his dedication to his students and to this program, and for ensuring our success in the program and in the future. Thank you.